So in this video, I wanted to go over a little bit about proton NMR, all right, which is written 1H NMR. I know that you've had a little bit about this, but I wanted to just refresh a couple things on how to use this technique to identify organic molecule structures. Okay, so first of all, what is the reason that you would see a difference in different types of hydrogens in molecules? All right, and the property that gets taken advantage of is the degree to which, so let's, just to get you oriented, this right here and this right here are both representing sigma bonds between a carbon and a hydrogen. All right, and you should know that in the bond there are two electrons that are being shared. All right, so that's what these two electrons are showing. All right, so this is just an isolated sigma bond, and you're going to have some other groups that are connected to this carbon as well. All right, it doesn't have to be three different groups, but it could be up to three. All right, and so the thing is that these other groups which are attached to this carbon can either pull electrons away from that carbon, or they won't pull electrons away from that carbon. And so what ends up happening is that if electrons are pulled away from this carbon, that's going to tend to take these electrons that are in this bond and pull them more towards the carbon. All right, and if the electrons are in that sigma bond are pulled away from that hydrogen, essentially what that's going to mean is that this hydrogen right here, or sometimes, and by the way, people use the term hydrogen and proton interchangeably. Remember, what's in the nucleus of a hydrogen atom is just a single proton, and that's why they call this proton NMR instead of HNMR. All right. So, but anyways, the more the electrons get pulled towards the carbon, the more exposed that proton is. All right. And the term for that is that it's de-shielded. All right. So what is said to happen is that the electrons have when the electrons are freely surrounding the hydrogen, it's considered to be shielded. All right. And why do we say shielded? It's shielded from the magnetic field that it's in. And recall from NMR, you have to use, for this to work, you have to put these molecules in a very, very strong magnetic field. All right. So the more these electrons are around the hydrogen, the more it's shielded from that magnetic field, and the more that they're pulled away from that hydrogen, the more de-shielded that is. All right. So if these electrons get pulled away, this is going to be relatively exposed. All right. And so it's going to be more de-shielded. All right. So since these electrons there's not a whole lot of shielding around it, this hydrogen would feel more magnetic field than it would if it had those electrons surrounding it. All right. So what about the case where if you don't pull electrons away? Well, if that's the case, there's nothing that's going to pull these electrons away from this hydrogen. So this hydrogen is going to be fairly well protected or shielded from that externally applied magnetic field. All right. Therefore, it's going to feel less of that magnetic field. All right. So some examples of this. Let's pretend that we're talking about an aldehyde. All right. So here's a hydrogen in that molecule, and take a look at this group right here. That's the carbonyl group that's part of that aldehyde. All right. And if you recall the electronegativities of oxygen and carbon, you'd recall that the oxygen is going to pull on those electrons a little bit more. All right, so that's going to have the effect of the electrons in this bond right here getting pulled a little bit more towards this carbon right here and away from this hydrogen right here. That's going to make that hydrogen relatively de-shielded. All right, so an opposite case would be something like the terminal methyl group on an alkyl group. All right, so let's say that we just have a kind of a chain of carbons, and at the very end of it, we've got this methyl group. All right, well, if you look at the types of bonds that are in this molecule, there aren't a lot of polar bonds. There's not a whole lot of things that are going to be pulling electrons away from this carbon. All right, so therefore, there's going to be nothing pulling any electrons away from these bonds right here. And so these hydrogens right here are going to be relatively well surrounded by the electrons in those sigma bonds. All right, and that's going to make them what's called shielded. All right, and so since they have that shield of electrons around them, they're going to be relatively protected from that external magnetic field compared to something that has those electrons pulled away. All right, so that's the basis on which NMR operates. All right, so essentially what happens when you look at the spectrum is that molecules that are relatively de-shielded, I meant to write that on this right here. So you can draw a left arrow and you can just write more de-shielded under that. And you can draw a right arrow over here and you can write more shielded. All right, so the more these electrons get pulled away from the hydrogen, which would lead to an relatively exposed hydrogen, the further to the left you're going to see the signals. All right, the more the electrons are left in place and are allowed to surround that hydrogen, the further to the right you're going to see the signals in the NMR spectrum. All right. One thing you probably notice about this is that this one right here is just a single peak, and that this right here exists as a triplet. I do want to point out that understanding the reason for the splitting here is an HL topic. As far as an SL level, just recognizing its location, all right? Recognizing that it's here towards the 0 rather than over here towards the 12 would be the only thing that you'd be required to understand. Okay, so all of the one thing about hydrogens in an NMR spectrum is that all hydrogens that have the same environment will have one signal. All right, and when I say one signal, realize that it's not the same as saying a peak, because this right here, this is one signal from a single type of hydrogen, but it's comprised of 3 separate peaks. All right, so what I mean by that. All right, if you take a look at this molecule right here, all right, there are 3 hydrogens on this methyl group, all right, but all 3 of these hydrogens would have the exact same chemical environment, all right, in terms of how they react to an externally applied magnetic field. They would react exactly the same way, all right. So in the spectrum, you wouldn't have 3 separate signals. You would just have one single signal that stood for 3 protons. All right. Again, also these 2 hydrogens right here are going to be equal as well. All right. So in terms of why that is, it's kind of easy to explain right here. If you realizing that you can rotate around this bond right here, you could rotate this so that this hydrogen would be in the exact same place that this one is right here. So it's kind of easy to see how these guys are all the same. All right, but just because 2 hydrogens are attached to the same carbon doesn't necessarily mean that they're exactly equal. All right, so for example, if you took a look at this molecule right here, and this would be one where we have, let's say that we have this chlorine, but it's sticking up on the top side of the ring. All right, well, let's take a look at these 2 hydrogens which are on the carbon right next to it. All right. Notice that this hydrogen right here is on the same side of the ring as that chlorine, all right? And that's because it's in this ring, and that ring doesn't allow complete free rotation around this bond, all right? So this hydrogen is on the same side of that ring, but this hydrogen right here is on the opposite side of the ring, all right? So these hydrogens would therefore not be the exact same in terms of their chemical environment. All right. In terms of NMR, this guy does not feel the same from a magnetic field as this one right here does. All right. So they would have 2 different signals. All right. So the other thing that you need to realize about interpreting an NMR is that when you have these signals, and if you take a look at this molecule right here, there's going to be 3 signals. One for these hydrogens, one for these hydrogens, and one from these hydrogens right here. The area under the curve, all right, so this is your thing. There's a certain area under this curve. Essentially, if I took a pair of scissors and I cut out this signal right here, and I weighed that signal, all right, the weight of literally the weight of that piece of paper would be 2/3 the weight of this signal right here if I cut it out. All right, and another way of saying that is just the area under the curve here is 2/3 compared to 3/3 for this guy right here. All right, or this is, if this is 3 units high, this would be 2 units high. All right, so the way that they represent the area under the curve is they put this little curve. All right, and we call that in NMR, we call that an integral. All right, we'll say that these peaks have been integrated, and that the relative height of these little things shows you how many hydrogens are causing that signal. So the relative heights here are 2, 3, 3. All right, and that comes from the fact that this signal is caused by these 2 hydrogens. This signal right here is caused by these, and this signal right here is caused by these 3. All right, so in just a second we'll get into why you have the different types of splittings, but for now just focus on the relative heights and notice how that corresponds to the number of hydrogens that cause them.